It's time to use our knowledge on how to do statistical tests and make confidence intervals to compare means. Well, what are we talking about when we talk about comparing means? We're talking about the difference between two means. Our estimate of this difference is taken from the sample mean of the first minus the sample mean of the second. And what we're trying to understand is the true difference between the first mean and the true difference of the second mean. So the top is what we would have with a sample. The bottom is the truth, which we don't know. Take, for example, batteries. Well, we have generic batteries and brand name batteries. And we would get a mean from these. Now, these are box plots, so they do show medians. We could have the mean for brand name. We could have the mean for generic. What are we trying to understand? The true difference between them. Should we be buying generic? Should we be buying brand name? On average, which battery lasts longer? Remember that this sample data is going to give us inferences into the truth of the population. So the sample mean y bar 1 minus y bar 2 allows us to estimate the difference between the means of the true population. This is what we are interested in understanding. We'll probably never know the truth for these batteries. We'd have to have all of them. We'd have to take a census. We are just trying to create estimates. So to do this, we need an amount of uncertainty. Now, we would love to use sigma, but we don't know sigma. Sigma is the true standard deviation for the first group, if sigma 1 is what we're talking about. We would probably only know the estimate from the sample. Sample standard deviation 1, sample standard deviation 2, which is the variation from the first group of batteries and the variation from the second group of batteries. We have right here the sample size from the first group of batteries and the sample size from the second group of batteries, and this whole equation creates the quantity known as the standard error of the difference. This is not an equation where we multiply things inside of it. It is a phrase, it is an idea, the standard error of the difference between the means. So it can literally just be called standard error of the difference. It is once again called standard errors because with standard errors, we use samples, and with the standard deviation, we would use the truth, but we don't know the truth. What we're talking about doing right now is a two-sample t. Notice that the two-sample t is only different from the one-sample t because it has two groups. In the two-sample t, it's very important to know you have a quantitative y variable of interest. All t's use a quantitative y. But the two-sample t has two groups and actually uses a categorical x. That's usually what really makes people say, what? Well, remember, the t-test is related to the y variable of interest being quantitative. So remember, when we're trying to measure something and understand a y variable of interest that is quantitative, we're doing a t-test. The two samples of it means there are two groups. That's why you get side-by-side box plots. Side-by-side box plots are the visualization we would use, or we could use stacked histograms or other graphical techniques. But should we be doing this? Well, we got to make sure they collected the data correctly. First, let's check our conditions. 1, did they randomly collect the data, which means they're independent, randomized samples. 2, are both sample sizes less than 10% of the population? We're not going to take all the generic batteries and all the brand name batteries. We need less than 10%, which we probably would have. Now we like to pause right here because the next condition depends on what data we're doing. Since this is quantitative, also a t-test, we are going to do the nearly normal condition. We'd actually have to check this for both groups, and a quick way to do this is just to glance at the histograms and see if they're mostly normal. And once again, you have to do this for both groups to see if both groups are nearly normal. The last condition states what it is. It's the independent groups condition. And with that, we are assuming, or at least have good reason to believe, that one group does not impact the other group. As in, if generic batteries were to last longer, it would not impact the brand name batteries to last longer. This is usually an easy assumption to make that the groups are independent. When would they not be independent? A classic example of this would be people on a diet. You have a before weight and you have an after weight. And this is what is called a paired t-test, which we are not doing, because these would be dependent means. We would not pass the condition. Because if somebody starts out a diet at 300 pounds, their after weight might be 200. Someone starts at 180, their after weight might be 150. And the weight after a diet would depend on the weight before a diet. So if you're comparing the means of these groups, the mean for group before, the mean for group after, the mean for the group after would depend on the mean for the group before. So that would not pass the independent. The way to check this condition is to say, does brand name batteries somehow influence the generic batteries to last longer? I don't see any way that could happen, so these are independent groups. Let's take a look at the confidence interval, which is trying to estimate the true difference. Once again, the first part of any confidence interval is an estimate. The estimate then has with it a margin of error denoted by the plus or minus. The first part of the margin of error is the confidence level denoted by the t or the z, in this instance the t for the t interval. It has a star because you get to pick it based on how confident you are. Next, we would go right here and find the standard error found by the equation down below. So the standard error is s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2 square root. A little bit like s over square root of n, where we're adding together the two standard errors and then square rooting them because we squared them to have them added together. You do not have to memorize these equations, at least for our classes. We would give them to you on a test. But do understand that it does show that if we increase the sample size, it will make the standard error smaller, which makes the margin of error smaller. If you have a larger t, you would be more confident because you're covering more area on the t curve. But the degrees of freedom here have changed. For the one sample t, which is not what we're doing currently, the degrees of freedom are n minus 1. I like to say for the degrees of freedom for the two sample t, the degrees of freedom are too complicated. So we use a calculator right here to find the degrees of freedom. Go ahead to the calculator and try using it to find out the degrees of freedom for the two sample t, which are too complicated to do by hand. You could do them by hand, but it's not too fun. So here we are right here with some data. The test has already been performed for us in JUMP, and we can see the interval. The interval has an upper and a lower of negative $26.94 to $113.96. But what were we analyzing? We were analyzing data from people offering to sell their camera to a friend or a stranger. And if you take a look, and this is key, friend has the negative sign. And the friend was offering to pay us less. And think about that. They're our friend, so we're maybe giving them a discount. And you can even see that in the data. I misspoke. If you take a quick glance at the data, you see that friends offered more. Just to review, the reason it's negative is because friend is higher. If you were to take a look and take guesses, you can see that the friend has a higher mean. I know we're looking at medians, but the mean looks to be close. Data is a little symmetric. So when the difference is negative, the second mean is higher. When the difference is positive, the first mean is higher. Key things right there. Don't reverse them. So since the difference is negative, the second mean was higher. Think about 10 minus 80. The estimate for the second mean was 80, and this would estimate the difference to be negative 70, which we see right here. So maybe these merely had 2's in front of them, like 280, 210, which is a difference of about negative 70. We're just guesstimating this right now, but this is how the mathematics is done. When we have a negative difference up top, then the estimate for the second mean was higher. When we have a positive difference, then the estimate of the first mean was higher, and I am 95% confident, 95 taken down here in the output, that the true difference between how much a friend and stranger would pay for the camera is that a friend would pay between 26.94 cents more to 113.96 cents more for a camera. Here's the mathematics followed through. If we do this by hand, it takes a bit longer, where we have to plug in everything. We have to find the difference between the means, which I did a pretty good job calculating right here. We have to plug in the standard deviations, which will be found right up here, and the sample sizes to get the standard error. So there is the standard error, and then we have to go and find the t statistic and its degrees of freedom. This is merely the degrees of freedom, and this is the page you saw below. You need the sample size for group 1, the sample size for group 2, the standard deviation for group 1, and the standard deviation for group 2 will be found in the output above. The degrees of freedom merely tells you the shape of the t. The shape of the t becomes more normal as degrees of freedom increase. So you'd go right here and put in the degrees of freedom are 7.6229. You'd ask for a 95% confidence interval, and you would get the following t-statistic. Now input all these numbers into the applet directly. And what is the next number on the t-statistic? This t is what we're going to plug into the formula for the difference plus or minus the t-statistic times the standard error. Find that. And here we are. Remember, this is our estimate of the difference. Then we simply go, margin of error is going to be the t-statistic, which is relative to the level of confidence we have on the respective correct t-curve with the correct degrees of freedom. And then we give standard error, which the standard error is the metric of uncertainty controlled by variation in the data. This then creates the interval, the estimate plus or minus the margin of error. Once again, the margin of error is everything after the plus or minus. It has been reduced to that. And then we have our estimate. And then when we solve it, we would get that we are 95% confident the true difference in the means, which is noted right there, is contained in the interval. And then we would state our interval. Now, we can also do statistical tests with this. To do a statistical test, we need to write a null and alternative hypothesis. So the key thing here is knowing the equation and what it means. This is what we are testing. We have what we observe in the data, and we have what we expect. In almost all instances, we expect a difference of 0. This is why a lot of times, since we expect a difference of 0, I just write the equation like this. So you don't need to know the delta 0 right there, or delta naught, is the difference or the null difference, because in almost all instances, we expect a difference of 0, especially for the math we'll be doing here. So we're merely taking what we observe and standardizing that difference. Standardizing it will turn it into a t-statistic. Do notice that this does not have a star because this is not one we pick relative to a confidence level. And then we have here the standard error is merely this equation that we've talked about previously. When we write our null and alternative, we need to use the proper notation. And the proper notation for this chapter will be the null states that the true difference between the means is equal to 0. When we do the alternative, the only thing that changes is the sign. We will either find evidence of it's not equal to 0, greater than 0, or less than 0. And it is the researcher's question that dictates the sign of the alternative. Going back to the previous output, we can see all three alternatives down here in the bottom. Is there evidence that our friends would offer different amounts? Yes, there is. Because the p-value is less than 0.05, and the first one right here is the does not equals alternative. The next one is the greater than, and then the less than. Take a look at those small things right there. Now, the first one has the absolute value on it, greater than absolute value of t, which would determine both sides. If you look very closely on the curve, you can see that the less than p-value is over here, and it's very tiny, virtually impossible to see when you shade to the left side of the curve. The does not equals would be double it, because you merely double this over to the other side, and 0.003 doubled is 0.06. The greater than alternative is the shading to the right side of the curve, and if you shade to the right side, you'd get the 99.7. Notice how the t-statistic is kind of close to 3, almost like 68, 95, 99.7. It's not exactly because the t is a little bit different, but still, we're out there on the edges of the curve, and we see a lot of area to the right side of it and very few areas in the tails. So the t is a great way to remember that it's a lot like the z when you look at the numbers. We can see the relationship's a little bit better right here in the output. Make sure to know where these p-values come from and how they are found. Another important thing to think about is what we've been doing with notation. Remember, we've been talking about the difference, and we've been standardizing it. Well, the difference is merely sample mean 1 minus sample mean 2. That's the difference. And then the standard error is standard error of the difference, and that is equal to the t-statistic. Well, wait a minute. That means this value right here, that t-statistic, is merely the difference divided by the standard error. So if you take negative 70.45 and divide it by 18.71, you will obtain that value. You can quickly draw this right here, telling you that that is equal to the t ratio when solving this out. This formula right here is replicated up there in the output. Degrees of freedom are also given to you in JMP, so it solves it out so you don't have to. The level of confidence for the respective interval is shown here, and the p-values according to different alternatives we can use down below. And with that, let's look at one more output here. Much shorter chapter because this contains a lot of the ideas that we've already been talking about. Let's think about running the full statistical test right here to see if students perform better on new activities with this data right here or worse. Maybe the professor has some sort of idea what's going on. He says, I think students are scoring worse on new activities. So they would say, my null hypothesis is that new activities, the true mean of new activities minus the true mean of the control activities is equal to 0. There is no difference. Notice how we're using this language up here and writing mu and substituting in an equal sign between them. Now they are looking for that they get worse with new activities. So if they got worse, the control would be higher. Does that make sense? Like for example, just making up fake numbers, if this was 100 and this was 90, we would get a negative difference right there. So with this, we would go here and put in the true mean for the new activities minus the true mean of the control is less than 0. First off, it didn't land less than 0 because it's not a negative difference. We wouldn't have evidence of that. Well, let's reverse it. You shouldn't do that. That's bad statistics. But for this example, let's do it. Let's see if there's evidence that the new activity is greater, has a higher mean than the control activities. Another way to write this, you venture out a little bit, is to put the equal sign between them, to say that they're equal, put the greater than there. Quickly, we could look at the p-value here for the greater than alternative and see the result from the JMP output. So now, running the statistics with a 0.05 alpha, we would say, I reject the null hypothesis that the true mean for new activities and the true mean for the control are equal, because my p-value of 0.0168 is less than my alpha of 0.05. This means I have evidence that the mean for new activities is greater than the mean for the control activities. Being able to write out your null and your alternative, being able to find the p-value by running the test is very important. The JMP output here allowed us to do the test very quickly by telling us the t-statistic relative to a t-curve with 37.27 degrees of freedom. Don't forget that this is the observed difference. We saw a difference of 9.9 points on average, and the new activities were higher because the first mean is if it's positive, we see a positive difference if it's higher. If it's a negative difference, then it's the second mean was higher in the observed sample data. Dividing 9.9 divided by 4.48 gives you the t-statistic. Remember, this is the difference, which is y bar 1 minus y bar 2, over the standard error of the difference right there. Make sure to practice. Lots to do right here, but knowing your notation is key. Good luck.